Good morning, everyone. Welcome to Lunch and Learn. This is the July edition. We're very happy to see you. If you are new here, you are in the right place. This is Lunch and Learn by the General Land Office and the Meadows Center for Water and the Environment. My name is Adriana Mendez. I am the Coastal Coordinator of the Meadows Center for Water and the Environment. I'll be facilitating today's presentation, and Brian DeSanti from the General Land Office will be introducing our speaker. And at the end, he will be assisting everyone with questions. We ask you kindly to keep your microphones muted. You may choose to keep your cameras on and off. That is entirely up to you. It is 11 a.m. right now. Let's give everybody else a few minutes to get in. As we wait for everyone to get in, please let us know where you're coming from. You can use the chat function, and I'm going to launch a polling so you can tell us, and we will appreciate your answers. So please go ahead. The poll is on now. I hope you can see it. Please let me know if you do not see it. We have had a few responses. Thank you for responding. We appreciate that. Okay, we're going to give folks a few minutes to get in. To log in, and we are ready. If you just joined us, good morning. This is Lunch and Learn, and we are ready to start. I'm going to end the polling right now. Please, everyone, if you feel like sharing where you're zooming in from, we will appreciate that. That'll be great. I'll use the chat function to do so.
All right, well, I'll go ahead and get us started, and if anyone else is pouring in, they can just kind of hop in as we go. Hello, everyone. My name is Brian DeSanti, and I'm a NOAA Coastal Management Fellow working at the Texas General Land Office. Earlier this year, we launched a new program called Clean Coast Texas, and the main objective of the program is to work with communities and jurisdictions in the coastal zone and to work together to enhance the management of non-point source pollution to improve water quality. Benefits from this include reducing illnesses associated with beach advisories and contact recreation on Texas beaches, and to reduce current problems with floodplain management issues and water quality where these two might intersect. If you haven't been to our website, we've got a beautiful website we've built, and it has a ton of technical resources that can be used for in these different communities. And we'll put the link in the chat shortly for our website. And you guys are at the Lunch and Learn series, and this series is designed to take our conversations from conferences and our professional work meetings and make them available to people in the communities that might benefit most from this information. I recognize quite a few of the names in here, but if this is your first time tuning in or you haven't seen any of our previous seminars, we've done other topics such as coastal bacteria along the Texas coast and harmful algal blooms. So please feel free to go back and check those out. With that being said, I'm excited to introduce this month's guest speaker. He's the director for the Texas Center of Climate Studies and the Texas State Climatologist, Dr. John Nielsen-Gammon. We'll be talking about extreme coastal weather events and how they tie into coastal water quality. And the one thing I want to do before I hand off the control is just remind everyone to please keep your mics muted. And if you have any questions, please put them in chat as we go, and we'll get to them at the end of the presentation. So, John, are you ready?
Sure. Yeah, thank you. So I'm coming from this as a climate scientist rather than a ecologist or water manager and so forth. So I imagine most people on the seminar are more familiar with specific issues of water quality than I am, but I'll at least give my take on the weather and climate impacts on water quality, and speaking about it in general terms as both the water quality within the coastal environment, as well as quality of water supplies for coastal communities. So there are lots of different aspects of weather and climate that affect water quality. I'm going to focus on extreme weather, and specifically 3 different types of extreme weather: drought, rainfall, and hurricanes. And there are other tissues I'll touch on as we go through these. They all illustrate some of the inherent problems associated with dealing with extreme weather impacts. First problem is they're fairly rare. I mean, we have hurricanes every year, but we don't have hurricanes hitting a particular location every year, for example. Drought is common, but extreme droughts are rare by definition. Extreme rainfall, same sort of issue, so that your own local experience in these sorts of extreme weather events may not be representative of the actual level of risk at your location, in your community, in your jurisdiction. And it may also not be particularly relevant to the long-term trends in these extreme weather events, because they're so rare that it's hard at a particular location to actually reliably determine how the risk is changing. You have to really look more broadly across a larger scale and long time periods to get at that sort of information. So an example of that is Texas annual precipitation, which has been increasing across the state of Texas, more so in eastern Texas than in western Texas. The map on the right shows increases of 10 to 21% over the past century and a quarter. Whereas in West Texas, trends are close to 0. In some places, trends are negative. Now, on the one hand, climate models project that that sort of trend is consistent with climate change. But the most consistent aspect is the tendency for East Texas to have more of a wetting trend than West Texas. But models disagree almost 50-50 on whether the average rainfall in Texas is going to increase or decrease. So the historical trend is an increase, and that you may consider that to be strong evidence that precipitation will continue rising. Or you may consider it to be part of some longer term weather cycle and evidence that precipitation will decrease. It's really difficult to pin down reliably any trends that are based upon just one line of evidence, like historical trends. If you've got historical trends saying one thing and climate models saying the same thing, then that increases the level of confidence. The third aspect of evidence that you really want to look for is a reason for the trend. Why should this particular trend that we seem to observe or climate models seem to project, why should that be caused by climate change in the first place? Now, with rainfall, it's kind of complicated. It's the product of the patterns of storm systems and moisture in the air and the whole bit. With something like temperature, it's a lot more straightforward. Obviously, if temperatures are going up globally, you would expect temperatures to increase on a local basis. And we see that here. Temperatures have gone up by a little more than half a degree Fahrenheit across the whole state per decade for the past few decades. And the 9-year running mean trend in Texas in the dark red line shows an increase at, on the long haul, about the same rate as the global temperature increases, and more recently at a somewhat faster rate. But we know why that's happening, and we expect it to happen. Now, let's look at those things in the context of drought now. So your experience of rainfall in Texas may be one of increased variability of rainfall. And if you look at the historical record of rainfall, well, gee, it looks like the over the past several decades, the wettest years have gotten wetter, and the driest years have gotten drier. But if you take the longer view of history, you see the swings we saw between 2011 and 2015 are just as large as the swing between 1917 and 1919. Just that people don't remember 1970 to 1919. Really, in Texas and most of the southern United States, for that matter, natural variability is the by far a bigger driver of changes in rainfall, even from decade to decade, than is something like climate change. And that variability has been around for a long time. There's evidence from models that it may be increasing, but it's big enough as it is, and the increases in variability is small enough that it's really not going to make much difference. If we're accurately estimating what the true risk is of drought and flood based on these historical precip, we're not going to be too far off going forward, at least for annual average precipitation. So, given what I said about rainfall, the outlook for drought you might consider that to be, well, may as well work with what's happened in the past. There's no indication that rainfall is going to especially increase or decrease overall. Rainfall is the main driver of drought, so our past risk is our future risk. And of course, drought affects water quantity, but it also affects water quality in the sense of it decreases freshwater inflows to coastal regions, which changes the rate, changes the concentration of pollutants that are flowing into the coastal regions. It changes the rate at which pollutants are flushed out of bays and estuaries. And typically, drought is also accompanied by higher temperatures and increased evaporation, which changes the salinity in coastal regions and affects water quality in that fashion. Because of the importance of evaporation, not just for salinity, but for the amount of water that's able to run off, temperature trends are also very important for drought trends themselves. And so the fact that temperatures have increased historically and are projected to continue to increase means that even if you have the same amount of rainfall at the same times of year, drought impacts will become worse because water is leaving the system through evaporation faster than it used to, which means you have lower stream flow, lower lake levels, increased salinity, and so forth. And of course, the higher temperatures are affecting also the biology of the marine systems as well, infecting algal blooms and so forth. So temperature trends are important for drought. You can go really as deep as you want into these issues, and climate models are useful for sort of integrating the different possible impacts of these different factors. Really, for drought, it's not just changes in rainfall, it's not just changes in temperature. Changes in rainfall extremes can matter because if you've got, say, tendency for bigger swings in summertime rainfall, then you'll have more frequent, more intense drought. If you have rainfall occurring more in winter than summer, that's going to affect the drought impacts quite a bit also. It's not all pessimism, by the way, on the side for wetting. Increased carbon dioxide means plants are using less less water when they're taking up carbon dioxide, so they have a more efficient use of water. So plant stress from drought may decrease at a given level of drought severity and water availability. But to put all these factors together, you really have to use a climate model in the absence of good long-term information on drought impacts, and which is usually lacking. So one example of climate model output is shown here. This is projections of soil moisture. The green is topsoil moisture, the blue is deep soil moisture. with the scale corresponding to typical magnitudes of natural variability in the past. So first message from a chart like this is soil moisture is projected to decrease according to climate models. That's somewhat useful information. You have to still translate that into drought impacts, but then you also have to look at according to what scenario and how certain is that. We don't have long-term soil moisture measurements. We don't have a good physical understanding of how these different trade-offs are going to sort out. So we're sort of stuck with relying on climate models. And because we only have that one line of evidence, anything we get from them has to be taken with a grain of salt. Next step, the scenario that's being shown here is actually the most extreme climate projection scenario. So it's sort of a worst case. This says that under the worst case scenario, topsoil moisture will typically be as dry as it is during a dry year in past climate. If what actually happens to climate is less severe than the most extreme scenario, then the decrease would be less. So this gives you a sense of the magnitude, and you can always adjust it in your mind based on what you think the what sort of target you want to plan for or expect. This green bar on the right is showing the range of the climate models between the say the quarter of climate models that are wettest and the quarter of climate models that are driest. So actually 1/4 of the climate models project an increase of topsoil moisture in East Texas, and 1/4 of them project a substantial decrease. And that variability in model output is probably tied to the fact that models don't agree on how much rainfall there'll be in the first place, whether that's going to increase or decrease. So unfortunately, with many types of extreme events, the challenge is dealing with the fact that we can say fairly confidently which direction things are going to be trending, but it's pretty hard, particularly with these complex systems, to say exactly how big the magnitude of that change is going to be. Okay, second type of extreme weather I'm going to talk about is flooding. And flooding impacts water quality in many ways. This is the rainfall from Hurricane Harvey, which produced 30 to 55 inches of rain over a fairly widespread area. People in the Beaumont area understand that impact on water quality pretty directly. This is the primary pumping station in Beaumont after Harvey, and it was knocked out of commission for a couple of weeks, I think it was, because it was inundated by floodwaters. So that's obviously a direct impact on water quality. There's a great deal of fear that flooding can introduce additional pollutants and contaminants, not just through the greater amount of runoff, but also the fact that you have water flowing through areas that have high levels of contaminants that don't normally get flushed. And so you end up with pollutants in the system that are normally locked in place on land. Now, Hurricane Harvey itself was the worst rainfall event in United States history in terms of the size of the area affected, the amount of rainfall, the duration of the rainfall. You can ignore the details of this plot. It's basically a bunch of rankings of the biggest storms on record. And Hurricane Harvey turns out to be the biggest storm on record, no matter how you rank things. It's the top of the list all the time. Other storms that affected other parts of the coastal areas also show up occasionally. Hurricane Florence in the Carolinas was a biggie, for example. But Harvey was, at least historically, the worst case scenario. And people have different meanings and interpretations of what worst case scenario is. If you're thinking worst case scenario is the worst thing that could possibly happen, well, think again. This is a reconstruction of what Hurricane Harvey's rainfall would have looked like if the storm had actually moved more slowly within the range of what was actually forecasted before the event happened. And uh, Houston is over here. If you're not familiar with the geography here, I've highlighted the Brazos River, which is the primary river through this area. And basically, the lower 120 miles of the Brazos River would have received a minimum of 45 inches of precipitation with this event. Totals going up to 60 inches, just based on a slight tweak of the actual storm track. And flooding in Fort Bend County was pretty bad as it was. There were people who were ordered to evacuate that couldn't evacuate because all the roads were closed at the time. Now, this represents almost twice as much rainfall there. So that could be the worst case scenario, except climate change is actually making extreme rainfall more intense based on historical trends and climate model projections and our physical understanding of how the climate system works. So that's one of the more robust trends we can look at. Extreme rainfall, just to start off with, is a big threat along coastal regions. This is a plot of what you estimate as the amount of rain you expect to see on the wettest day of a century, according to data within individual counties across the region. And you can see that the totals are much higher along the coast than they are inland. That is primarily due to the impacts of hurricanes, but not entirely. Basically, anytime you have moist air, moist, unstable air flowing from water to land, it's going to hit the land, which is this rough surface, and it'll slow down. And air basically piles up on the coastline and has nowhere to go but up. So coastlines are great for triggering thunderstorms and forcing extreme rainfall to happen right in the coastal zone. And that's what we see with these extreme rainfall tendencies. If you aggregate them over multi-county areas, that tendency still shows up. Typical once in a century rainfall amounts are around 10 inches inland, whereas they're or 8 to 10 inches inland, whereas they're like 12 to 15 inches along the coast. And the largest, according to the historical record, is in southeast Texas, where Hurricane Harvey happened. And that's literally partly because of Hurricane Harvey happening there. We can also analyze the trend in extreme rainfall. And what we see is, in general, an increasing trend. The percentage increase in the magnitude of that once in a century rainfall has increased on average by about 15% over the past 60 years. And that sort of trend is expected to continue for the reasons I mentioned. Warmer atmosphere holds more water vapor. And so the risk from flooding, all other things being equal, will also increase. Now, the actual risk of flooding, of course, depends on what flood control measures we put in place. And historically, we've improved our flood control measures at the same time as we've improved, well, at the same time, flood risk has increased. So those sorts of things are somewhat of a trade-off. I'll give you an example of that. The Harris County Flood Control District was created because of massive flooding during an event back in the 1930s where floodwater invaded downtown Houston. Well, that flood event, that rainfall in that event was nothing compared to Hurricane Harvey, but Hurricane Harvey's floodwaters ended up reaching approximately the same level in downtown Houston. So all of the flood mitigation measures weren't enough to prevent a flood, but at least they've improved resilience over the long haul anyhow. But as the risk of extreme rainfall increases, the need to allow for and be able to tolerate increased amounts of extreme rainfall will become important also. Now, this is an example on the left of how those sorts of calculations get done. Basically, we take the wettest day of every single year and fit a statistical distribution to it that is allowed to change with global temperatures. And you can see visually an increase in the sort of the upper magnitude of the event that might be expected, as well as the magnitude of a typical event. Excuse me. And this is an example from Harris County where Houston's located. And it's really dramatic increase. Hurricane Harvey is this point up here. This is just one day totals at a single station. There were places that, of course, are much wetter than that. But you just go to the coast, go south until you hit the coastline, you hit Brazoria County, and you see almost no trend there historically. And we have this one event that was pretty impressive back in 1979 that actually in other stations set the record for one day rainfall in the United States. Now, it would be a serious mistake to conclude from this that rainfall risk will continue to increase in Harris County and rainfall risk will continue to stay level in Brazoria County. First off, a lot depends upon the history of events. If we put these on the same scale, actually, Harris County's risk hasn't really caught up to Brazoria County's risk based on this assessment. Probably Brazoria County risk truly is higher because it is a coastal county, whereas Harris County is like one row inland. But if you look at these long-term trends I showed you earlier, these variations, even on a regional scale, are much smaller than anything that climate change itself would produce. Climate change might cause increased trends in the eastern United States compared to the western United States, but it's not going to cause things to happen on a finer scale. That's weather. Could be individual events, could even be variability from decade to decade. But going forward, you really need to look at what's happening over the whole region and say, yeah, overall, it's about a 15% increase, and that's what to expect. And it's still a challenge to say 15% increase over what? Really, it's a 15% increase over what the risk used to be. But do recent events properly measure risk, or do they underestimate it? Again, it's challenging because we have a short record. Probably Harris County is actually pretty darn prepared for climate change going forward because they've had experienced such a dramatic increase, and they probably perceive that to be all due to climate change rather than partly climate change and partly natural variability. Whereas I don't have it up here, but a place like San Antonio, or to take a coastal example, Tallahassee, hasn't experienced a big trend in extreme rainfall, and consequently, their perception of climate change's changing risk is probably behind the curve compared to how those risks are growing. Okay, third and last type of extreme weather event I want to talk about are hurricanes. These are the sorts of trends you hear about. You know, we have this generalization that climate change is making extreme weather worse. So far, I've talked about two types of extreme weather. I've talked about extreme rainfall, which I've argued climate change is making worse. And I've talked about drought, which I've argued might be making worse by climate change, but at any given location, it's not entirely clear whether that will in fact happen. There are other types of extreme weather that climate change is making better, actually. Despite what you might have heard, climate change is almost certainly making extreme cold temperatures less likely to occur. So the odds of an event like the February cold in Texas and Louisiana are actually decreasing, even though a lot of people probably think that climate change is making extreme cold worse also. Even some scientists do, but most lie into the making it better camp in that regard. So these are all things you might have heard about hurricanes. What does climate science say about what's really going on with those? Well, it varies. Um, Increasing number of hurricanes, the evidence is quite mixed there. We don't actually, as scientists, have a good explanation for why the number of hurricanes is what it is, let alone why it might change. And there's so much variability with hurricane frequency from year to year, and we only really have good numbers of hurricane frequency since the satellite era started back in the 1970s. So we have to rely on climate models, but they don't really tend to simulate hurricanes. They're kind of too coarse in their resolution. Hurricanes are too small for them. But they're simulations of hurricane-like phenomena. Most of them say fewer hurricanes going forward. What about stronger hurricanes? That's that seems like it's probably going to be in that direction because we have a physical understanding of how climate change would affect the maximum intensity of hurricanes. So how can you have, so this combination of more hurricanes and stronger hurricanes, how does that play out? Here's an example from a climate model study. And I want to use this to show you what it means to have, say, fewer hurricanes, but more intense hurricanes. So this is the maximum intensity based on a simulation in black of the current climate in this climate model. And then the red is a century later. And this particular model actually didn't simulate much change in the number of hurricanes. But you can imagine, but it did simulate a change in the intensity so that the distribution shifts toward larger maximum intensities. And it's not much of a change, in terms of how close together these curves are, but think of it in terms of the frequency of 150 knot hurricanes. This was saying about a 1% chance in the present climate, and it's saying more than a 2% chance in the future climate. So this is a factor 2 increase. Get down here, we're actually talking about a factor of 5 increase in category 5 hurricanes. So this apparently small increase in average intensity corresponds to a big increase in the frequency of those extreme events. And that's actually usually how it works for extreme weather events. A small shift in the average leads to a large change in the frequency of the extremes. Now, so imagine if the number of hurricanes actually decreased by a factor of 2. That would be an enormous decrease in the number of hurricanes. At 150 knots, a factor 2 decrease in the number would mean 150 knot hurricanes would be just as common in the future as they were in the past, because the shift toward more intense storms would be countered by the shift toward fewer storms. But as you go farther out in the distribution, even if you cut the number of intense storms in half, it would still be more than we had in the present day climate. So this is just a sort of a hypothetical exercise to show how even if you have fewer hurricanes overall, you could still have an increase of category 4 and category 5. And it's just because the average intensity of storms could be changing. Okay, what about a larger storm surge? Well, that's tied to stronger hurricanes. And it's also tied to sea level rise, because even if storms were the same intensity, if you have higher sea level, you have a higher storm surge. I worked out the numbers once for the Gulf Coast, and the general rule of thumb is suppose you've got a facility that's designed for a storm surge at a particular level, and was built in, say, the 1960s. Given the rate of sea level rise and coastal subsidence, and ignoring the loss of barrier islands and that sort of thing, which also affects vulnerability. By the year 2050, the risk to that facility will have doubled simply because of sea level rise's impact on storm surge. So even though sea level rise is measured in millimeters and centimeters, it's still a substantial risk at those extreme thresholds. So that combination of factors means it's a pretty good bet that we'll get larger storm surges. What about storms moving more slowly? There was a paper that came out a few years ago that said, yeah, they're going to slow down. They have slowed down, actually. But subsequent studies have said that there's not really, there's some evidence that points in the other direction. In fact, for Texas in particular, the risk of stalling storms may actually be decreasing because of how climate change is affecting larger scale weather patterns. And I've already talked about intense rain. It's not just intense rain from all causes that increases, it's intense rain from any given cause. And climate change affects intense rain from hurricanes, both from the fact that hurricanes will be carrying more water because it's warmer, but also because hurricanes will, according to climate models, become more compact. So the same amount of rainfall will be happening over a smaller area. Okay, what's the risk for hurricanes and water quality? Well, many aspects of risk to hurricanes and water quality. For example, the February winter storms illustrated, once again, the importance of electrical power for water supplies. So that affects water quality if you no longer have potable water. In the natural environment, storm surges could do things like wipe out lots of storage tanks in the Houston Ship Channel area and spread contaminants far and wide, which would have a long-term lingering effect on water quality until those pollutants that then get deposited over a large area are mitigated. Changes in hurricane intensity can also affect, actually sea level rise itself affects not just the hurricanes itself, but also water quality in a sense, because it's bringing ocean waters to places they didn't used to exist because of sea level rise and coastal retreat. It's affecting the balance of freshwater and saltwater in the bays of Texas as well, because it's affecting the exchange of water with the sea. And in estuaries, which are, of course, freshwater on top, saltwater beneath, sea level rise means that the level of the salt water is going up similarly, and that's going to affect saltwater barriers in estuaries to protect water supplies. So here's a plot of historic trends in sea level globally. And there's analyses have gotten better and better at this. And it's gotten to the point where we can actually break down the different causes of sea level rise. One cause is the ocean's getting warmer. Over here on the left-hand panel, we got the sea level rise at the bottom, and the two components of it. Orange is the ocean's getting warmer, which means the water basically expands. And then the red is water being added to the oceans. Oh, where's it coming from? Well, it's coming from glaciers. That was a big cause of sea level rise early in the 20th century, but as we start losing glaciers, we actually start losing the amount of water coming from glaciers to the ocean. Meanwhile, we seem to be triggering enhanced loss of water from the ice sheets of Greenland and Antarctica. So that's so far very minor, but potentially an accelerating factor. There's a lot of good evidence it's accelerating. Man has had an impact on water as well. Historically, it's had a decrease in sea level because we've been locking water up on land in reservoirs, which keeps it from being in the ocean. But reservoir building has sort of slowed down globally, but groundwater pumping has continued, and groundwater pumping is having a net result of taking water from below ground and putting it in the ocean. So that's now a very minor contributor to sea level rise as well. But all those factors adding up, it's put it all together, it's clear that sea level is increasing, and it's clear that sea level will continue increasing and at a gradually accelerating rate. So far, again, this is the global plot, 150 millimeters of sea level rise, so about 8 inches or so. That's going back 120 years. Along the Texas coast, the total rate has been probably twice that because of coastal subsidence. And I think more than that in Louisiana, less than that near Florida. So it varies quite a bit spatially how local land is rising or falling. But that's all going to be an impact on top of what's happening globally. Okay, so to summarize here, we've got possible increases of drought plus definite increase of evaporation rates from bays and estuaries leading to higher salinity and other potential water quality impacts. We have extreme rainfall increasing. That's clearly happened historically. It will continue to happen, which increases the variability of rainfall inflows and also increases risk to infrastructure and consequent impacts on water quality from that. And some aspects of risk from hurricane are also increasing with different levels of scientific confidence, depending on the particular aspect of hurricanes we're talking about. And those also can have potential variety of impacts on water quality in coastal regions as well. So that's what I prepared for you. I'd be happy to answer questions.
All right. Hi, everyone. Yeah, please put your questions in chat and we'll start going over them. But while people are typing, I can go ahead and start off with a question. You mentioned that Brazoria County, their relative risk has not increased over, time, as where the Houston area has, it looks like it has increased quite a bit. Can you speak to some of the factors there that might be causing, Harris County to, have an increased risk while Brazoria County is just kind of staying, relatively the same?
Sure. Well, I would actually argue that the risk has increased at a similar rate in both locations, but the actual events have evolved differently in the different locations. For example, Hurricane Claudette in 1979 produced most of its rainfall south of Houston, whereas Hurricane Harvey in 2017 produced a lot more rainfall in Harris County than it did in Brazoria County or Galveston County, for example. But there's nothing about climate change or any other aspects of man's impact on the environment that would lead us to expect that if Hurricane Harvey had happened in 1979, the rainfall would have been closer to the coast, or if Claudette had happened in 2017, the rainfall would have been farther inland. And there's also nothing to suggest that storms like Harvey have become more likely, while storms like Claudette have become less likely. So that difference in the history of extreme rainfall in Brazoria County compared to Harris County is at least mostly due to the different years in which the extreme events that affected those locations actually happened. That being said, there are also possible factors that could lead to an increase in risk in Houston that's larger than other areas. But we wouldn't be able to identify that from the historical record because it's it would be too subtle compared to the impact of natural variability. Those factors would be impacts of the urbanization. Just like coastlines are a good locus for precipitation because they force air upward. Well, buildings also slow down the air, so that could cause an increase of flood risk. And pollution also affects how rainfall gets produced within the atmosphere differently. So that in the fact that Houston is now a much more urbanized environment changes the amount of pollution in the air, and it can change the amount of rainfall. I should say finally that you may get a different answer from some other scientists, because there have been a couple of studies that have argued that there's actually a fairly substantial increase due to Houston being Houston. My personal assessment of those is that they're not very reliable studies. I have some objections to the techniques they used, which I could talk about offline. But so my personal opinion is natural variability is much more important in those changes and trends that we've seen historically than is any sort of driving factor.
All right. We've got a question from Charlie Henry, and he's asking, is the federal government moving ahead building the spike? Sorry.
That's probably supposed to be spine, but yeah.
Okay, along the Gulf Coast to prevent storm surges.
The federal government is doing a study of the issue. Army Corps is looking at different options, as far as I know, for Houston. I haven't followed it super closely. I imagine someone else probably has, but I think the study is expected to finish in the next year or so. I wouldn't call that moving ahead, however, because moving ahead would imply that they're actually committing to doing something as opposed to studying it. And there's, a huge price tag associated with this. It's something that could conceivably fit under a massive federal infrastructure bill, which I know is being talked about. But whether it does or not, whether it falls in that category or not, has certainly not been decided. So I would not characterize the current state as moving ahead. There's a lot of work to be done politically before moving ahead would be a fair description.
All right, and we've got another question from, I'm gonna butcher that, so I'm gonna go ahead and skip the pronunciation of that. And wants to know, are some of the global trends of sea level increase also true in Texas coastal regions?
Yeah, so we got global average trends, which is what I showed. In Texas coastal regions, well, I talked about three factors. I talked about sea level trends and coastal subsidence. You could actually break the sea level trends themselves into two factors. One is the global average, and the second is the local manifestation of that. And give you an example of that. If Greenland melts, which it's sort of in the process of doing slowly right now, that increases the amount of water in the ocean, but it also makes Greenland less heavy, and so you end up having the land surface rise near Greenland, and in response, you end up with more sea level rise farther away from Greenland. So you got those effects going on. That sort of effect is pretty small for the Gulf Coast. So global sea level rise is a pretty good guide for what the ocean is doing along the Gulf Coast. But the other aspect of it is what's the land doing? And we've seen subsidence along at least the Texas, Louisiana coast because primarily of extraction of groundwater and oil and gas and that sort of thing. people have become more aware of that issue in recent years. And so I think that extraction is being managed better and is going to have less of an impact. So bottom line is we may see sort of competing influences. The effect of subsidence will decrease, whereas sea level rise globally continues accelerating. And that may translate into basically a sustained pace of sea level rise for the next several decades on the Gulf Coast.
All right, thank you. We've got an update from Diana Ramirez, said that the coastal Texas study, Coastal Spine, the final report in the EIS will be finished this year, and they sent it to Congress. So Congress must approve and authorize the funding for it to be built. I'm not seeing any more questions pop up at the moment. I've got another one. Will the intensity level of the 2011 drought be back in Texas in a few years after some wet years?
Yeah, good question. We know that Texas is a droughty state. 2011 was only marginally drier really than say 1917 or 1956. So that amount of rainfall deficit seems to happen, a few times a century. So that will almost certainly recur. Don't know when. It's not like it's a regular 50-year cycle. As much as we would like drought to come in cycles, that's sort of a misnomer. It does what it does pretty erratically. But the thing that really set 2011 apart was the higher temperatures that went along with it. Texas, Oklahoma set a record for the United States for hottest summers in 2011. We were several degrees warmer on average in the state of Texas than in any previous year, including 1917 or 1956. And with average temperatures increasing, that means that temperatures during drought will increase also, possibly at accelerated rate. There's possible reasons that might happen, but we don't know that for sure. But in any event, that means that when we get another year as dry as 2011, it's probably going to be even hotter, which means greater evaporation, soil moisture dries out faster, groundwater depletes faster, base flow in rivers and inflows to bays and estuaries drop off to zero faster. And even though the state of Texas is trying really hard to manage river flows and groundwater flows, past history has shown it's relatively easy to make plans, but when you get to the point of having really serious water deficits, those plans can go out the window because people start really getting desperate and stakeholders get desperate, and that's happening at the same time that the needs are the greatest. And so I expect droughts worse than 2011 to happen in the future, but unfortunately no telling when.
Thanks for the great explanation. So at this time, I'm not seeing any more questions, so I just want to thank everybody for coming out. Thank you, Dr. Nielsen-Gammon, for providing all this information for us and expanding further on it. And I just want to let everybody know we're taking next month off. We're not having a lunch and learn seminar. We will be returning in September, so be on the lookout for some more information on that. And before we let everybody go, I'll turn it over to Adriana to put the poll to see if you aren't currently receiving updates from us, please let us know.
Thank you, Brian. Thank you for joining us today. Here's the poll. We will appreciate your input. It helps us serve other people. So if you could take the time to answer, it's only one question. Thank you so much, everyone. Be safe, and we hope to see you next time. Take care. Bye.